let's talk a little bit more about vibrations and how this is applicable in the laboratory environment, for example. So one of the things that we have to remember about how group theory works is it can tell us about all of the molecular vibrations that we have in a molecule. So remember we said that for a nonlinear, we could talk about all 3n minus 6 vibrations, or for a linear, we would have 3n minus 5. Vibrations can be measured in a couple ways. The one that we're most familiar with is down in the Orgo lab. We use the FTIR, where we're using infrared radiation, but we know that an infrared active mode only results if there's a change in dipole moment of the molecule. That sounds useful because we learned about how we could find dipoles from point groups. Now we know the symmetry of vibrations. There's probably a good connection we can make here. Connection seems a little bit cumbersome at first, but it's really pretty simplistic. A vibrational mode that has an irreducible representation that has the X, Y, or Z label is IR active because this shifts the center of the molecule. That might sound a little bit odd in the end here, but really this is just a combination of what we're talking about. It's saying, hey, how does the dipole moment respond to that vibrational motion? And so when we see a shift in the center of that molecule, that is what we're looking for. So back to our good old friend water here and the C2V point group. We saw that the symmetric stretch had an A1 symmetry to it. And we see the A1 transforms with Z. So therefore, we would say that this mode is IR active. If we look at the next mode that we have here, the asymmetric stretch is the B1 symmetry. We'll go down to B1. There's our X transform. So it is also active in the IR. And the final one over here, the bending mode transforms as an A1 irreducible representation. Again, that is the Z, so this mode is also IR active. So in the case of water, all three modes are IR active. So we should be able to see them in an FTIR scan, for example. Now, the thing that we have to remember here is this example, all the modes, all the vibrations were IR active, but modes don't have to be IR active. That is not a requirement of a vibration. In the case of water, we didn't have that because our vibrational modes were A1, B1, A1. But let's take a look down here. If we found a mode that was an A2 representation, it doesn't have a Cartesian label down here. So A2 modes are IR inactive. In other words, if we had a mode that transformed with A2 symmetry, we would not see that in the FTIR spectrum. It doesn't exist there. There is another way to learn about vibrational modes, and that is through Raman spectroscopy, and we'll talk about that in another video. But basically, to be a Raman active, it has to have some combination of these symmetry functions. So basically, these were the d orbitals as we labeled them earlier, but these transform the same way as Raman activity, and we'll talk about what that means in another video. So if we were to look here in the water, A1, B1, A1, so here is A1 and here is B1. Note they both have these features here, so all three are Raman active modes. In C2V symmetry, we could also note that the B2 and the A2 also have these components here, so all these modes in a C2V molecule, all of them are Raman active. So that's kind of interesting because we say all of the modes are Raman active, but we noted in the previous case, A2 modes were IR inactive. So some spectroscopies don't see everything, some see different parts of things. And the real kick in the pants here is that a molecule does not have to have any features that are IR or Raman active. Some modes we say are silent. So we'd have to find a place in the character table where we don't have XYZ or we don't have the linear combinations over here. But that's not to say that silent modes can't be observed ever. There are other spectroscopic methods where we could do a combination of electronic and vibrational excitation so that we could see them. we're not going to worry about that here. It's just the note that, okay, we don't have to have necessarily a Raman or IR active band to know about the vibration. There are other ways we can learn about the system. So that's what I wanted to talk about here. We'll see some examples of these coming up here, but just kind of the basic understanding of what modes are IR active, what modes are Raman active compared to their symmetry, so that we can use that in upcoming cases. All right. If we have questions about this, let me know. We'll get you cleared up as always. And until the next time I see you, be excellent to each other.